Yes, sir.
Yes. Okay. So you can see here from the answer, yeah, the probability that a patient recover from a blood rare blood disease is 0.4. 0.4. If 15 people are known to have contacted diseases, what is the probability that at least 10 survive? And then B, 3 until 8 survive, and the C, exactly 5 survive. From the E, yeah. So first, you have to identify that the from this case, let's draw some to say some initial information from the problem. So the probability that a patient recovers from rare blood disease. So the probability, let's say P, probability success or recover, probability recover is equal to 0.4. And when the probability not recover is Q, let's say Q is 1 minus 0.4, of course, and then the result is 0.6, okay? If 15 people are known to have contacted this disease, what is the probability that at least 10 survive? So at least, please point out here, at least 10. At least 10, it's mean that probability at least 10, yeah, equal to, so it's gonna be the X is the member of X is 10, 11, 12, 13, 14, and 15. Yeah. How about the 9? 9 is not possible because at least. So we should clarify this point. Okay, because of at least, so we draw the mathematical expression being X greater than or equal 10. Okay, until this, I hope it is clear. And then it is equal to the probability 1 minus probability X less than 10. Okay. Yeah. Actually, in this solution is written like this. Is there any other solution? So, of course, from this expression, it's mean that, yeah, from this expression, for example, we can draw the probability, or let's say in this the probability. So is kind of 10, 15, 0.4 plus, yeah, probability 11, 15, 0.4. So it's kind of like this. And until what? Until probability 15, 15, 0.4. Yeah. Or also, if using this expression, it's mean that we compute the probability minus probability. We compute from 0, 15, 0.4 plus, and we make a square bracket, and this is probability 1, 15.04 and so on until the maximum is probability 9, 15, 0.4. 4, and the result is, so that's why mathematically we can draw being like this. Please notify this one. Yeah, this one. And result of this point is 0.9 something, and minus 1 minus 0.9 is equal to 0.0338. Okay. Okay, I hope it is clear. Yeah, and then for the probability from 3 to 8, 3 to 8, mathematically, please notify here, this is 3 to 8. It means that greater than or equal 3 and less than or equal 8. So in this case, we should compute being like this. Yeah, of course, it is possible to, for example, from this point, we can use calculation from the probability 3, 15, 0.4 plus until probability 8, 15, 0.4. Yeah, okay, from this point. But it's also similar with the computation 0 to 8 minus 0 to 2. Yeah, something like that. So it's gonna be like this. Okay. How about this one? This one also x equal to 5. Yeah, it's similar to the probability 5, 15, 0.4. Yeah, something like this. If you can compute directly, but indirectly you first compute 0 until 5, and then subtract by 0, probability 0 until 4. Yes, yes, and the result is like this. 0.4, 0.2, and the final result is 0.1, 59. Okay, okay, that's all the result. I already explained. Anyway, any questions?
Sir, I
Yes.
still don't understand the notation, like B, how to read the notation of it, like BX15 0.4.
Okay, okay, very good questions. Okay, yeah, actually we have not introduced this kind of notation. I'm sorry, because I will summarize at the end. But yeah, actually the notation like this, B X 15, 0.4 is a formal notation to compute probability from binomial distribution. Binomial distribution. Yeah, okay. What kind of expression actually? Yeah, if we draw this one, can you see, yeah, everybody, yeah? This is a graph. It's kind of a binomial distribution, and the y-axis, it always the probability of x. Yeah, this is x. So this binomial, yeah, I changed the color here. So representing the, for example, this is given 15 combinations, yeah, 15 combinations from 0 until 15, yeah. So how the probability, how much the probability at the x equal to 0, x equal to 0, and then how much the probability x equal to 1, 2, 3, 4, 5, 6, 7 until 15. And then if we compute for the, let's say, the probability 0, 15, 0, 4. Probability 0, 15, 0, 4. According to the binomial distributions, we can compute. Wait a moment. I want to show the something that actually from this. It's similar to it's similar to 15 combination 0 that the probability P equal to X, it is the X is 0, the Q, this is the N is 15 minus 0. It is a combination of 15 factorial. This is 0 factorial, 15 minus 0 factorial multiplied by the P, probability P is 0.4 powered by powered by 0, and this is 0.6 powered by 15. And then it is equal to 15 factorial divided by 15 factorial, and this is 1, and 0.6 powered by 15, it is this is 1 and 1, and this is I need to calculate. I need to calculate. Wait a moment. It's similar to, not similar, but powered by oh no. 0.6 powered by 15, right? It's around 0. Okay, 0.00047. Yeah, the result is 0.00047. Okay. So this is for x equal to 0, and then using using similar way, so the probability I prefer using the blue one. Okay, the probability of 1, 15, 0.4, it is like a combination 15, 1 power by 1, p power by 1, q 15 minus 1. Okay, so it is like 15, this one 1 factorial, and this is 14 factorial, and then this is 0 by 4, 0.4, and 0.6 power by 14. Yeah, so this is 15 is correct, and this is a 0.4, and this is 0.6 power by 14. So we can calculate is a 15 multiplied by 0.4 multiplied by 0.6 power by 14. It's around not around, yeah, but exactly 0.0047, something like this, for x equal to 1. And then you can compute for the probability 2, 15, 0.4, and probability 3, 15, 0.4 as well. Yeah. Is that any is that clear, or which one which is not clear yet?
Oh, so the x is like the number of the people that is recovered, the one that we want to find, the probability.
Probability, which one?
For the, so from the notation, the x is like the number of the recovered people from the disease, the one that we want to find the probability. Is it like that? Oh,
okay.
So it means that sigma x equal from 0 to 9, so which means that we add up all of the probability from the 0 to 9.
Yes, add up given this definition sigma.
Okay. Thank you,
anyway, I have a question. Do you know why this should be sigma?
That is total.
Yeah, total. Why this is a total? Why we only compute the probability 9, 15, 0.4?
To compute the probability of an event that didn't happen, that shouldn't happen. Is it correct?
Sorry, can you repeat?
To compute the probability of the event that shouldn't happen.
Should not happen.
Yes.
Should not happen. Should not. Yeah, it seems to be correct, but yeah, it seems to be correct. Yeah. Because based on this, actually, it's come from this expression, mathematical expressions, the x less than 9. So we compute all the possibility that the X is less than 10, less than 10, sorry, yeah, less than 10. It means that if you back to the graph, let's say from this short equation is this is around 4 by 10 power by minus 4, right? And this is for the one is 4, yeah, 4 10 minus 3, maybe something, I don't know, maybe it's kind of like this the probability, yeah, and then 10 and then decreasing. Okay, and then computing the x less than 10. So let's say this is 10 here, so this is 15 here, 10 here is add up. This is 9, this is should be add up, this 9, this add up, this one, this one, this one, this one, this one, this one, and this one, this one, this one, this one, until the minimum. So that's why it should be a probability less than from 0 to 9. Yeah. Okay. Okay. Is that clear or not? Or somebody is still asking, or sir, I have a question still because I still confused something.
Sir, is there a faster way to count it? I mean, looking from the equation, it seems not time efficient. Is there
Yeah.
like a shorter way to count it?
Oh yeah. Okay, wait a moment. I should clear this up. Okay. Anyway, there is a way to compute this equation much shorter using what we can call a binomial tabel. Binomial tabel. Binomial tabel binomial tabel. Okay, let's see. Actually, I have, but I will search in the internet. Binomial tabel. So the base the probability is 0.4, and then for the n is 15, 15, 15, 15, 15, and then is 0.0, 15. The R is 9. 0. So the probability of success in independent trial. 0.4 for the P is 15. This is correct. 0. Standard normal. Wait a moment. I have to check the book. I have to check the book for the table. Binomial P is something and 0. Oh no. 0999 seems to be correct, but binomial probability distribution. Oh, this is binomial. Binomial tabel CDF. This one. So the probability n-nya 15. Mana 15? 15. Okay, seems to be correct. Okay, this one. Okay. 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 Wait a moment. Actually, I miss sequence how to this explanation. It's better to me to show the something that yeah, formal definition. Maybe I will explain this one before we discussing a bit more about the exercise. Can you see my screen now?
Yes, sir.
Yes. Okay. So right now I will explain the formal definition of binomial distribution. Remember yesterday that you already conduct the case, yeah, the case, and then we already compute, yeah, you remember this is for the point 3 until 6, point 3 until 6. So this one, yeah, for the 3, so this is the number of defected chips. Let's say this is the number of defected chips every from 3 trials, from 3 taken 3 chips. So the possibility that there is no defective chips. There is 1, there is 2, and there is 3. Okay, actually for the 0, the member is no. Okay, for the 1, the member is change the color, defective, no, defective, no, defective. This is the member for 1. Okay, until this point clear?
Clear, sir.
Clear. Okay, and the n, ddn, and ndd. This is for the member of this one. How about this? The 3 is ddd. Okay, this point. Okay, yeah. And if you remember that for this one, the probability is the probability for being n. Can you help me? How much? Hello? Hello,
Wait,
everybody.
sir.
Is it 0.75 0.75 power by 3?
75 power by 3. Okay. Okay. Yes. How about the 2?
Yes.
Sorry, I mean the one for x equal to 1
422.
is equal to is probability, so dn plus probability n dn plus probability n and d. It's is kind of 0.75 power by 2 multiplied by 0.25 times 3, because 3 times. Is it okay?
Yes, sir.
yes, sir.
Yeah, everybody got it, yeah? So, wait a moment, 475 power by 3 is equal to, this is around 0.42, 0.42, yeah. Maybe it's better. 0.42, and for this one is power by 2 times 0.25 times 3. Also, this one is 0.42. How about this? Is it correct? (0.25 times 3). Okay, and this one for P2, it's mean that probability dn d probability dn probability and d and dd. Okay, so it's kind of 0.25 power by 2, 0.75 times 3. So let's calculate 0.25 power by 2 times 0.75 times 3 is kind of 0.14. Is here 0.14. How about the last one is kind of 0.25 power by 3. This one is 0.015. Okay. Okay. So you can see now that this is the probability of X, right? Everybody can see? Everybody understand about this? This is a probability distributions. Specifically, this is a binomial. Binomial, okay? Binomial probability distributions. Okay. Okay. Why this is a binomial? Binomial because each point, when we calculate each point of x, we can use the formula. It's kind of 3. This is x. This is probability power by x q 3 minus x. So each point here is 0, 1, 2, 3. The probability we can compute using this formula. Until this point, clear?
Clear, sir.
Yes, sir.
Anybody have a question or still confused? And this is the discrete probability distribution, specifically because binomial is always discrete. Because we are now talking about the discrete probability distribution. You see here 0, 1, 2, and 3, and the range become higher if you can see, if we not only take 3 chips, it means that we take more than 3 chips, the spectrum getting higher. Okay, until this point is clear?
Yes, sir.
Yes. Okay. So back to the formal definition, you can see here the formal definition, particularly for the graph here. You can see here, it's similar graph actually. You can see this is the x, the x-axis, this is the x, this is the x representing the, how to say, the combinations, any possible combinations, the x. So and the y-axis, this is the probability. You can see here, let's say from the blue one, please focus to the blue one. The blue one, the p is 0.5. That's the probability, let's say a success, and then the probability not success is just a minus by 5 is 0.5, let's say something like that. So given the n equal to 20, so the maximum spectrum is only until this point. You can see here the blue one is the maximum until n equal to 20. Okay, and 20, and the result is, you can see here, from this point, this point, this point, this point, this point, and this point, 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 until, and then decreasing again until this point. You can see here is like a bell shape, but in discrete manner, in discrete manner. And each point here, we can compute the probability using this formula. Actually, this formula is perfectly same what I already explained before. You can see here, this is actually the expression of combination. The nx is actually the combination of what? Nx. It's similar, similar way. And this part actually, it's similar to the power by x, and q, this is the complement, n minus x. Okay, is that clear? And another expression, maybe to actually this expression to identify this x is the x-axis here, the n is actually the any possible combination, at the time is 3, Kalau yang sebelumnya berarti 3 chips, ini menunjukkan 3 chips, 3 chip. And the p, this is the defective is belong to definition, tergantung definisinya. Kita menyebutnya p-nya ini sebagai apa, begitu. Is that clear about about this explanation, formal definition about the binomial distributions?
I think yes.
I think
Yeah,
clear, sir.
clear. Okay. And you can see here, when n getting larger, also the spectrum, you can see the red one. The spectrum is increasing. It means that, let's say, in one trial, in one picking up the chips, we pick 40 chips. Yeah, this number indicating that phenomena. And you can see the distribution is almost similar. Yeah, almost. I mean, the pattern is similar, but the maximum probability is decreasing. Yeah, because we have a spread. So getting, how to say, yeah, spread. Yeah, getting the slope is not so sharp. Ya. Tidak terlalu curam ya, jadi melandai gitu loh ya. And then when we talking about the probability distribution, we always deal with the mean and the variance. These two parameter is mandatory for probability distribution, for discrete case or continuous case. And then by the formula, we can actually you can check by yourself by adding each point here, and then divide it over the range. Yeah, you can check by yourself. But mathematically, you can see here that the mean of this kind of distributions, binomial distribution, is just multiplication between any possible variance, any possible combination, and multiply by p. P is probability, yeah. And about the variance is just npq, something like that. Okay. So it will be many times for the problem or question, banyak pertanyaan akan menanyakan tentang mean dan variance dari probability distributions. Ya, karena why? Ya karena sebuah random itu biasanya akan ditanya rata-ratanya berapa, kemudian tingkat variasinya dari datanya itu berapa. You can see, for example, in the distribution of grading lah, ya. Misalnya dalam satu kelas hasil kuisnya kan ada yang 50, kemudian ada yang 70, ada yang 80, ada yang 100. Nah, biasanya kita akan tanya rata-ratanya hasil kuisnya berapa sih? Nah, untuk menentukan kita pada posisi di bawah rata-rata atau di atas rata-rata. Biasanya begitu. Oleh karena itu, it's usual for asking or asking how much the mean or how much the average of the distributions. Sebagai contoh, misalkan pendapatan per kapita masyarakat Indonesia, kan itu artinya dari batas bawah sampai dengan batas atas, from the minimum to the maximum. The spectrum is so large, but in general, in terms of maybe helicopter view, dalam artian misalkan kita sebagai presiden, kita akan bertanya, emang rata-rata pendapatan per kapita Indonesia berapa? Nah, yang ditanyakan rata-ratanya kan, seringnya begitu, karena dia random. Kemudian pertanyaan berikutnya, variasinya berapa sih? Kesenjangannya berapa? Tingkat kesenjangannya, tingkat beda-bedanya berapa? Nah, itu biasanya parameter yang penting juga ketika melihat sebuah random variable. Kemudian yang kadang ditanyakan adalah batas bawah sama batas atasnya berapa sih? Gitu. Biasanya begitu. Itu those kind of parameter that are usually useful to take some analysis. Yes. Okay. Is there any questions about this formal definition about the binomial distributions? Please, if you have questions.
Sorry, I think you haven't answered my question, how to count it faster. Is there a way, to count this equation faster? You said binomial table.
Okay, yeah. So it's good. It's good question. And then is there any way to compute this kind of formula? Okay, very good questions. And then allow me to. Okay, I will show you how to say. Yeah. Actually, we have. Yeah. Allow me show you to the some internet. Yeah. Stop start screen, and then I will change this screen and. Yeah. Can you my screen here?
Yes, sir.
Yes, sir.
Yes. Okay. First, you should write probability distributions, but I forgot to say binomial probability distribution tabel. Okay. And you can click this one, and this is the tabel. You can see here, this is the binomial distributions, and you can see here, this is the formula. You remember, this is combination, yeah. Maybe some of you asking, yeah, asking, sir, why this combination is a bit different? You mentioned that this is NR, yeah, it's similar. It is another way to compute the formula R. Yeah, it's similar. Yeah, I hope it's not make you confused. Okay, about the next part is also similar. Okay, so you remember that this is the probability distribution. This is the X, and this is the probability of X. Okay, actually, this is the X. No. I a bit change. This is in this case is the X is R. Yeah, this is R. But I am following this one. This is the R, probability of R. Yeah. I chose this one. This is the R. The X-axis is R. The Y-axis is probability R. So you can see here. Let's say. Let's say n, and in case of 3 chips, so n equal to 3. Is it correct? So when n equal to 3, how about when the r equal to 1, equal to 0? 0. Let's find out the 0, 1. N first is n equal to 3. Okay, so we spot this point. N, this is n3, and then how about the r? R is equal to 0. So we should point out here. So in the previous case, when p equal to 0.25, so we should point this one, p. 0.25 is around this one. This one. This one. Okay. You remember that our graph is actually the computations. Yeah, it's based on the formula. The formula is 3 combination 0. Probability 0.25, yes, power by power by 0, and this is 0.75 power by 3, right? Because 0 minus 3 minus 0, it is equal to, if you remember, is 0.42, and is perfectly matched to this result. Is that any questions? This is how to read a table.
For me, it's clear, sir. For me.
Clear, yeah? Everybody, how about the others?
Clear, sir.
Sir, so the one that you showed us is like exactly like the table?
Yes.
I mean the graph, yeah, exactly like the graph?
Yes.
Oh, okay.
Yes. Okay. So, binomial probability calculator. I think I like this one. Okay. You can also check by compute using this one. Okay, wait a moment. Okay, clear this one. Okay, you remember? Yeah, this using, yeah, you can use a calculator, of course. Wait a moment, and then okay, probability success on the number of success. Oh, okay. Okay, actually this is P. So in this case, in our case is 0.25. Okay, this is the P. The number of trial is 3. Oh, no. This is computing the calculator will compute binomial and cumulative probability. Okay, no problem. So when x is 0, it should be 0. The result there, the result it should be 0.42. Let's compute for this one, yeah, for this one. That's the result. Okay. Any question? Is it clear to use a calculator? Yeah, I prefer this one. How about this one? We can change also 1. Yes. It's changing. Yeah, it's almost similar. Yeah, 0.4. How about the 2? It's exactly same what we already calculate last time. Okay. How about the 3? Yes, one. Okay. Everybody, yeah, you get it?
Yes, sir.
Okay. Is
Yes,
it clear?
sir. Clear.
Clear. Okay, good. And then, so back to the slide. Yeah, sorry, it is a bit takes time, but I prefer to make you understand clearly. So yeah, please take the time not to, yeah. So can you see, this is actually the probability of each component. Yeah. How about this one? This expression already clear or not?
Yes, sir. For me, clear.
Clear, yeah. When we computing at least 10 survive, means that we should compute, yeah, the x is including 10, 11, 12, 13, 14, 15. Okay. Is it clear? Okay. Okay, and then actually we can compute the probability when 10, 15 0.4 plus probability 11, 15 0.4 plus until computing probability 15 0.4. And you can compute using the table, also using calculator for each part, calculator, okay. How about this one? And this one also same, yes. So it is no problem, How about this one? This one is another component actually. You can see here, this is 10, we computing the probability and sum up together from 10, 11, and 12. And then this is another component actually, another component from 0 to 9. And that's why this should be put 1 minus this component probability, okay? And then the result is this one. Okay, I hope this is clear. And then actually this is another way. I will tell you more. You can see here that actually back to the formal definitions, you can see this is a probability distribution function, and there is another another graph you can see as a cumulative distribution function. This is cumulative distribution function, or CDF. The cumulative, how to compute the cumulative? Actually, for example, in this point is a cumulative, means that we should add up the previous probability. Maybe it is not so clear, so I would like to open the binomial distributions at the Wikipedia. Wikipedia is no problem. Okay. And you can see here, and I copy the image and I passed here. You can see now. To make it exactly same scale, so you can see now the upper is probability distribution. Let's say this is the probability distribution function, and the lower is cumulative. The meaning of cumulative means that we accumulate the previous X. You can see, that's why you can see the red one. Please compare the upper and the lower. You can see until this point. Okay, until this point, the point probability is still increasing, but then saturated. You can see the saturated is 1. Because when you add up together in this point, the result it should be 1. So everybody, can you? So in this point, it should be 0.5 the probability, because you add up this point add up, sum up, So the result in this point is 0.5. And then increasing until the maximum is 1. Okay, is that clear? How to read the two graph? What is the differences between actually this is probability distribution function, and the lower is cumulative distribution functions. Can you distinguish between two graphs? Everybody?
Sir, I still don't understand why like the graph for the binomial graph, the graph is like a curve, like a bell curve, but for the cumulative distribution, the curve is like going up and then getting flat. I mean, like different.
Okay, actually, this graph is originally we can say both are binomial, ya, oke, both are binomial. Jadi dua-duanya ini sebenarnya binomial, tapi yang atas itu probabilitas, yang bawah itu kumulatif. Oke, kalau probabilitas berarti untuk setiap nilai X di sini menunjukkan nilai probabilitasnya gitu loh. Menunjukkan nilai probabilitasnya. Tetapi kalau di sini yang bawah nilai X ini menunjukkan kumulatifnya. Jadi contoh nih ya, saya apa namanya? Misalkan saya ingin menghitung CDF dari 10 dan PDF dari 10. Itu kalau PDF dari 10 ya dia hanya menghitung probabilitasnya si X ketika sama dengan 10. Tetapi ketika CDF 10 itu sama dengan menghitung probabilitas atau PDF 0 ditambah PDF 1 ditambah PDF 2 sampai dengan PDF 10. Paham sampai sini?
So it's like the total of the probability.
Top?
The total of the probability.
Yes, total but less than or equal 10.
Total of the probability from 0 to 10.
Yes,
like
exactly.
Oh,
yes.
Okay.
Yes. And then
Okay.
the total is you can put here in this, in this point.
Oh, okay, sir. Thank you, sir.
That's why we call kumulatif. Itu kenapa kita menghitungnya sebagai kumulatif. Kumulatif kan berarti ya akumulasi gitu lah. Gitu. Dari yang paling bawah sampai dengan yang paling atas gitu. Kemudian mungkin some of you asking about why the cumulative is not compute from the maximum. Let's say ya kalau gitu ngitung CDF dari atas sampai bawah boleh dong. Ya sebenarnya boleh, tapi konvensinya atau aturan yang sudah disepakati kalau CDF itu menghitungnya ya dari bawah sampai dengan nilai paling atas yang diberikan. Gitu sih, ya. That's the point. So again, I make a clear, hopefully it's more clear. When you talking about the PDF of X, actually we are only computing the probability at this point. But when we computing the CDF of X, we compute the probability of X and less than X, and then sum up together. That's the differences between the probability and cumulative. Okay? Okay. I hope it is clear. So that's then Dan ekspresi ini, this expression is kind of CDF 9. Everybody agree?
Yes, sir.
Yes, sir.
Yeah. So, and there is a calculator ya. Ada kalkulator yang langsung bisa menghitung CDF dari CDF-nya gitu loh. Kita lihat back to the calculator ya. Oh, where is the calculator? Okay, let me show you calculator. So here the probability is 0.4. Okay, P 0.4 ya, remember ya. And the number of trial is 15, right? 15 trial based on the exercise, yeah. The number of success is 9 because 0 to 9, and then calculate. You see, please point out this, yeah, this one. Cumulative probability. This one, yeah, this one. You see the mathematical expression, this one. It's similar, but you'd see the mathematical expression is totally different. In this case, 9 is not include, but in this case, 9 is include. So the result is 09666. Okay, remember 09666. Back to the PowerPoint. Which one? This one. 09666. Okay, it's completely same with the calculator that we already compute. And yeah, we just must subtract one, subtract by 09666. The result is this one. Okay, so I hope now you clear. That's why we changing from this form to this form, because actually this one is computing the CDF. This one also the computing the CDF. This one computing CDF2, yeah, CDF2, and this one computing CDF8, right? That's, and you know that for the point C, the probability at 5, yeah, is already compute more easy to compute using calculator, yeah, but directly at the point 5. But another way is like a CDF5 minus CDF4. It's similar. Okay. Any questions?
Sorry, sir, but why -4? Yeah?
Minus
Why is
4.
it
You mean
minus?
this one?
Yes, yes.
Yeah, okay. We are computing what?
The probability of exactly 5 survive.
5 survive. Only
Yes.
5, yeah, not less than or equal.
Oh, okay.
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 Okay, only at 5, not CDF. Yeah.
Yes.
Yeah. So
I get it.
yeah. That's why this is 4. You get it?
Yes, because that's the probability that we're not looking for, right? The probability that shouldn't happen. Yeah, basically I get it.
Okay. Any other questions? Yeah, by now, we already discussed about the binomial distributions, probability, the how to say, the pattern of binomial distributions, also the CDF, CDF binomial distributions, and the case when we applying binomial distributions, okay, how to compute the probability binomial distribution mathematically and conceptually from the graph given the problem and exercise. Already, okay. Anyway, let's move forward a bit to we will talk about a bit, hypergeometry distributions. This is another distribution, but it's similar with the binomial, but the case is the differences is in this statement. In the binomial, the number of population is constant. It means that the constant, that with replacement very large or infinity, and then otherwise for the hypergeometry, the number of population is reduced without replacement or limited. Hence, each trial will reduce the total number. Actually, contohnya begini. Kalau kita misalkan sebuah kartu itu kan the total is 52 kan, dan total number is 52, yeah. If we take 5, misalkan kita ngambil 5 kartu secara acak, 5 kartu, berarti nanti kan sisanya tinggal berapa ya? Tinggal 47 kan sisanya. Sisanya tinggal 47. Terus kalau kita ngambil lagi 5 lagi, kan basisnya berubah ini. Kita lihat dari 42 menjadi 47. Nah, ini untuk kasus hipergeometri. Tetapi kalau binomial, ketika ngambil 5, nanti dibalikin lagi ke sini. Jadi ininya bukan 47, tapi tetap 52. Dibalikin lagi, ngambil dibalikin lagi, ngambil dibalikin lagi. Nah, kalau yang hipergeometri ngambil ya sudah terambil, berarti kan sisanya kalau nanti mau ngambil lagi berarti sisanya tinggal 47 gitu. Kasusnya di mana? What kind of case that follow like a hypergeometry distribution? Yeah, we have a limited sample or limited population. For example, misalkan mobil lah ya, mobil kita akan tes, kita misalkan ada 50 mobil, kira-kira kita akan ngetes crash tingkat keamanan untuk airbag dan lain sebagainya. Berarti kan kita harus ngambil satu mobil untuk dihancurkan. Berarti kan nanti sisanya cuma tinggal 49. Kita ngambil lagi, dihancurkan lagi. Misalkan ini hasilnya belum memuaskan, kemudian kita melakukan eksperimen lagi, satu mobil lagi dihancurkan lagi. Gitu. Artinya mobil ini kan sulit untuk di replacement atau alasannya another reason is because of expensive, ya, for example. That's kind of a real scenario for hypergeometry, and that's why you can see the example here. This is the example of hypergeometry distribution. If we wish to find the probability observing 3 red cards in 5 draw, jadi mengambil berapa kemungkinannya mendapatkan 3 kartu itu merah dari 5 pengambilan, ya. From ordinary checks of 5T2 playing card. The binomial distribution in section 5. The binomial distribution does not apply unless each card is replaced, ya. Kalau di binomial 5 kartu ini akan dikembalikan lagi ketika ngambil, begitu kan, is replaced. The deck resolved before the next draw is made. To solve this problem, sampling without replacement, it means that we keep the 3 reds. Let us restate the problem. If 5 cards are drawn at random, we are interested in the probability selecting 3 red cards from 26 available in the deck. Why 3 and why 26? 26 actually, the red one is 26, right? Only the half, right? Actually the red card is, we can choose from the 26 available, right? Or the half of 52. And the 2 black card from 26, the rest, the remains. And then actually, basically, we are selecting 3 belong reference to the 26. Jadi kita ngambil 3 dari kombinasi 26. Dan yang kedua ini mengambil 2 dari kombinasi 26 juga. Ini yang komponen hitam. So in this case, the total ways to select 3 red, 2 black cards in 5 card actually is multiplications. 3 and 2 belong to 26 and 26, yeah, and divided by this one. That's why this is a combination, this one, and this one. And this actually, this how we compute based on the factorial, yeah, and then we can compute this result. That's the point of hypergeometric distributions. Okay. Okay. Back again to slide 5. Actually, we have a case for the Poisson distributions. I have a case. This is some result of experiment. Given the experiment from 6 until 12 p.m. for counting number of vehicle passing through. Jadi ya, kita membuat eksperimen. Actually, this data coming from some experiment counting the number of vehicle passing through. Yeah, the table show the observed traffic. Yeah, show the pattern of the traffic, number of cars during every hour divided into 120 time slot, which is per slot is equal to 30 seconds. 30 seconds, and then the number of yellow background, yeah, you know, this one is the number of time slot, yeah, and then compute the total vehicle here in this cell, and then average of the vehicle in this cell, and sample the vehicle of this cell given this data, this row, yeah, you can see here. For example, yeah, how to read this data actually. This is the time taken of the data from 9 to 12 p.m. And this is the number of vehicle passing through. No vehicle, one vehicle, two vehicle, three vehicle, and equal or greater than 4 vehicle. And then this is the time slot. This is 27 time slot. That's no vehicle. There is a 38 time slot with only one vehicle. 30 slot for 2 vehicle, and so on. For the time between 7 to 8 p.m., this is the result. 8 to p.m., this is the result, and so on, and so on, and so on. And then the task or the question is, please compute the total vehicle for this time. Compute the total vehicle between this time, yeah, in this time. Compute the total vehicle in this time. Also compute the average for each time slot, how many vehicle, and compute the variance given the data. Okay. Okay. Any questions? Yeah, actually we are we have running out of time. Yeah, we are running out of time. So I make you assignment. Actually, this is the first assignment. The group. Yeah, I would like to assign the group assignment here. This is group 1. This is group 2. This is group 3. This is group 4. 5, 6. So there will be 6 group. Each group computing this one, this one, this one. Second group, this one, this one, and this one. Okay. Any question? I will divide you into 6 group.
Sir, I have a question.
Yeah.
I still don't understand what time slots mean.
Time slot. 1 hour is divided into 120 time slot. Until this point, clear?
Okay, yeah.
So each time slot consists of?
Okay, 30 seconds.
Yeah, 30 seconds. So what's the problem?
So the problem is like I don't still understand, especially for the vehicle frequency, like how to read it. Like, yeah.
Which one? Which one? Which one?
Like 0 and then 27 and then 37.
No. You should sequentially, if you asking 0, you should asking 1, 2, 3, and 4. You understand about this one?
So is it like, so there are 27 time slot that the number of the vehicle is 0? Is it like
Yes,
that?
perfectly, something like that.
Oh, okay. Okay.
So
Thank
this
you, sir.
point, what is the meaning of 38?
So like there are 38 time slots that only has one vehicle.
Yes, perfectly.
Okay. Okay, thank you, sir.
Yes, you're welcome.
So, sir, how should we count the total vehicles? Should we like 1 times 38 and then plus 2 times 30 and so on and so on?
Okay. Yeah, you should explore this. Sorry.
Okay.
Yeah.
Yes, sir.
That's the assignment.
The assignment. Okay.
Yes. So, okay. Any question? Any question? No? So, I don't know how many people you are. 16? Is it correct? You are 16?
I think so,
Yes.
sir.
I think so. Okay. But not everyone here, yeah? Not everyone attending this class. Okay, no problem. Oh. Okay, I will show the group apa? I should save the pictures first, and then the desktop is a temporary bagian group. Okay, seems to be good on sound. Yeah, and then Probstat document, and then download temporary, and then I have a picture. Where's your picture? Picture group. Where are you? Where are you? Oh, this one. Okay, this one is good. Great. And then this one pembagian group. Okay, sip. Okay, I have uploaded the group grouping for conducting this assignment. So, have you seen? Maybe a bit to open this photo. Okay, photo, and then I would like to change this one. Okay, can you see? No. Okay. Okay, can you see, yeah, the group, yeah? You can see here nomor absen 1 sampai dengan 3 become one group, 4 and 5 second group, and so on and so on. Yeah, some of you have 3 members, some of you has only 2 members. Yeah. I cannot divide maybe in same number, yeah, because the total is not so perfect. Yeah, so the total is 6 groups, something like that. And then the group divider I already uploaded at a group at WhatsApp, so please check it. And then please submit the assignment at AMAS. The announcement will be available after this course. Yeah. So, any questions?
Sir, when is this assignment due?
Huh?
When is the assignment due? The deadline?
Either you mean the deadline? The deadline, a letter will be announced at AMAS. Yeah, I'm not considering yet right now.
Okay, sir. Thank you, sir.
Yeah. Okay. Any other questions? No questions. If no, yeah, we finish our class today. Thank you very much for your attentions. I hope we still a good condition forever. And see you next week. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam. Thank
Thank
you,
you
sir.